Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at examining series in calculus using TI Technology. I see that many of you are joining us for the first time, so we'd like to offer a special welcome if this is your first T-Cubed Professional Development webinar. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make those tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists tonight, Vicki Carter and Tom Dick. Vicki has been teaching high school math for 40 years and currently serves as the math department chairperson at West Florence High School. She is co-chair of the AP Calculus Development Committee and serves as a question leader at the AP Calculus reading. Vicki has served on TI Inspire authoring teams and has presented at many international, national, and regional conferences in the areas of technology, calculus, and statistics. Vicki, thanks so much for being with us.
I look forward to talking with everyone tonight.
And Tom is a senior mathematics advisor for Texas Instruments and is also professor and former chair of the mathematics department of Oregon State University. He has served on the editorial panels for the Journal for Research in Mathematics Education and the Mathematics Teacher Educator. He remains active in the College Board's Advanced Placement Calculus program and has previously served as chair of the AP Calculus Test Development Committee. He has been recognized by the Mathematics Association of America with its Distinguished University Mathematics Teaching Award for the Pacific Northwest, and in 2008, he was inducted by the Oregon Council of Teachers of Mathematics into the Oregon Mathematics Education Hall of Fame. Tom, congratulations, and thanks so much for being with us.
It's great to be here, and I'm looking forward to the webinar.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send questions to Tom or Vicki using the Q&A window on the right side of your screen. As a reminder, this session is being recorded, and at the conclusion of the webinar, we'll provide a link to the event certificate of attendance. We hope you don't have any audio issues tonight, but if you do, try selecting Communicate in the WebEx browser window and then choose Audio Broadcast. If that doesn't help, in the participant window where you can find your name, in the lower left-hand corner, there's a phone icon. If you click on that phone icon, it'll allow you to call in using your phone as opposed to using the audio broadcast. And that should improve things if you continue to have issues. At this point, Vicki is going to discuss our agenda.
Well, tonight we've already had our welcome and introductions, and tonight we're talking mainly about series and BC calculus. We are going to briefly talk about tests for convergence, but mainly what we're going to do is show you some documents where you can investigate series with your students, both with the TI-84 and the TI Inspire, and we will also look at the Maclaurin and Taylor series, especially those series that the students are supposed to go into the AP exam knowing, which would be 1 over 1 minus x, sine of x, cosine of x, and e to the x. We'll talk a little bit about radius and interval of convergence, and at the end, some online resources and the webinar giveaway.
Thanks, Vicki. And Tom is going to discuss our expected outcomes for tonight.
So we're going to do a brief summary of what the main topics in BC Calculus are around the topic of series and kind of highlight some of the key changes that have recently been made in the Advanced Placement BC course description regarding series. Then we're going to head into the technology and hope to share with you some opportunities as well as help you understand some of the limitations for exploring series both numerically and with the computer algebra system. And we'll be illustrating those with both the TI-84 and TI Inspire. Especially besides numerical series, we'll look at graphically Maclaurin and Taylor polynomials, and that's a really powerful use of the visual technology using both the 84 and the Inspire. And in that context, as we talk about convergence of Taylor series, we'll take a look at how we can investigate graphically the radius and interval of convergence for power series. Should be a fun night.
Thanks so much. Vicki, it's all yours.
Okay. All right, let's go to the next slide here. All right, so I hope you're all familiar with the new framework that we have for AP Calculus, and big idea number 4 is on series, which is exclusively a BC topic. And there are 2 enduring understandings in the framework under the series, the big idea of series, and that is that the student will understand that the sum of an infinite number of real numbers may converge, and the other one is that a function can be represented by an associated power series over the interval of convergence for the power series. And we have a number of learning objectives under each of those 2 enduring understandings, but essentially what's outlined on this page is directly from the course description, and these are the things that the students need to be able to do with series as they go into the AP exam.
So just kind of summarizing the various tests for convergence that students are expected to be familiar with and be able to use, probably the simplest one is the nth term test. And that's really a test not so much for convergence, but divergence. So if you have a series and the nth term doesn't approach 0, then there's no way that series could converge. So that's definitely a test for divergence. If the nth term does go to 0, then that's where all these other tests will come into play, because you really don't know what's going to happen. There are series where the terms go to 0, some diverge, and some converge. Alternating series test is a very nice one because it's, I think, one of the simplest ones to apply. So if you have terms that alternate in sign and the nth term approaches 0, and the terms decrease in absolute value, then that series converges. All 3 of those conditions are really important to have, and so you can actually create counterexamples with if you violate any one of those. Now, the alternating series error bound, that's listed as one of the new things in the course description, but it's really something that's not so much new in its usage. It's new that it's actually being referred to by name now. And the alternating series error bound is just if you truncate an alternating series, a convergent alternating series after n terms, then the very next term, its absolute value, is putting a worst case of the error. So the error can't be any larger than the absolute value of that next term.
Okay, we also have the absolute and conditional convergence as a new topic. I think most teachers of BC Calculus have always talked about this with their students, but there are now going to be questions that are directly about conditional convergence and absolute convergence as pertains to these alternating series and other new series that we can obtain. So thinking about like the geometric series with your nth term as being -1/2 to the n power, that converges absolutely, as opposed to the alternating harmonic series that converges conditionally. And of course, we know that the the harmonic series diverges, so the alternating harmonic series converges conditionally.
Some other tests for convergence that are tested on in the AP exam is the integral test. And that relates a series to an improper integral. So your nth term of a series, if you can think of that as a function of that index n, and f is non-negative continuous and monotone decreasing, then it's tied very closely to the improper integral in the sense that the series of those terms is going to converge if and only if that improper integral from 1 to infinity of that function converges. The limit comparison test is new to the AP course description. So it's not a new test mathematically. It's been around a long time, but it is a new topic. And it relates, I guess, it's a way to take your knowledge of a series you're familiar with and use it to compare to a series that's unfamiliar to you. And here is if you have two series and you form the ratio of the terms, term by term, if that approaches a finite positive limit, then those two series have to behave in the same way. They either both converge or both diverge. Something I tell my students along those lines is it's like the harmonic series diverges. Even if you multiplied all the terms by 1 over 1 million, it's still going to diverge because it's similarly, if you have a convergent series, even if you multiply that by some huge number like 1 billion, that's still going to be a convergent series. The ratio test is one that's not only used for numerical series, but it's also going to come into play as you go into power series. And the ratio test is looking at the ratio of the n plus first term over the nth term and the absolute values of those and seeing if that approaches a limit L. If that limit turns out to be less than 1, the series converges absolutely. There's that new term. And then if L is bigger than 1 or doesn't exist, then the series diverges. Interestingly, if the limit is exactly 1, you need to start looking for another test. Okay. By the way, on the ratio test, this it's really rooted in the geometric series, which is probably the easiest and best understood series because we can not only test its convergence so easily, we can actually find its limit fairly easily. And ratio test is really comparing a series to a geometric series.
Vicki, it's all yours. You can go ahead and share your desktop.
Okay. All right, so the first thing that we're going to look at is on the TI Inspire, and this is going to be a series exploration, and we'll do a little bit with this, and then we'll go over to the 84 and look at a few things that we could explore that are similar to this. This is just the introduction page. So, Tom, do you want to talk about our table here a little bit?
Sure. So one thing that you can do numerically with series, especially to illustrate the distinction between the sequence of the terms in a series and the partial sums, is to use the spreadsheet. And we'll also take a look at how this could be done with lists on the 84. So what we've done here is this is the spreadsheet on the Inspire behaves very much like an Excel spreadsheet. And what Vicki has here is in column A, she has just entered the index starting with 0, going up 1, 2, 3, 4, and so on. And what we're illustrating here is suppose our series is a geometric series where we're taking 1/2 to the k power, and you can think of the value of k as our index, and that's that 0, 1, 2, 3, 4. So you can see that sequence of terms is going to be 1 to the 2 over 0, so that'd be 1, then 1 over 2 to the first, 1 over 2 to the second, 1 over 2 to the third, and so on. So we can see the individual terms there. The partial sums is really, they constitute a new sequence. So the sequence of partial sums is what we're examining in that column C. And so what that is basically a cumulative sum of the items in column B. So we have 1, then 1 plus 1/2, then 1 plus 1/2 plus 1/4, 1 plus 1/2 plus 1/4 plus 1/8, and so on. And then that's what we're looking at is, does that new sequence of partial sums have a limit? And if it does, we call that the sum of the series. So I think that spreadsheet is a very nice way to take a look at and get really a sense of that distinction between the sequence and the partial sums. By the way, I think that's one of the things students will trip up on is sometimes mistaking convergence of the individual terms in the series with convergence of the sum.
Yes, and I totally agree with that. And looking at this table or this spreadsheet, I think it makes it much clearer to the students kind of how that those nth partial sums are building and how they can think of they've looked at tables to estimate limits when they first started the course almost, and so now they can look at that column C and think, okay, as n goes to infinity, do these nth partial sums, do they approach a particular number? And I think that's very helpful to the students.
So I just realized, Vicki, maybe I didn't draw attention to it, but if you go up and highlight that first entry in column C.
Oh, okay.
If you look at the bottom, notice that that entry is defined to be equal to just B1, the first entry in column B. But as you move down to the next cell, it says, okay, let's take that sum just above and now add on the entry in B2. And then what was done here is we just did a fill down like you can do in a spreadsheet, and now that's mimicked that formula, updating the indices in a way. So now we take the sum that was in C2 and add on the next term in the sequence. So it's a really natural way to think about building up that sequence partial sums.
Okay, you ready to go to the next page, Tom?
Well, yes, let's do that, and then before we
okay.
go on to the 84, yeah. Okay.
All right.
Now here, we're actually, this is something that could be done on either TI-inspired CAS or non-CAS, is actually looking at specific partial sums. So if you do a numerical partial sum to a specific index, you can sum that up. So what we have here is an illustration of a math box that has 1 over 2 to the k, starting out with k equals 0, up to n, and n has been attached to a slider. So right now, n is equal to 1. You can see that over in that left-hand pane. And so this will really give us the 0th term, which would be 1 over 2 to the 0, plus 1 over 2 to the first. So the first two terms would add up to 1.5, which is 1.5. Now this slider, it's set up, now we can just increment and go up to n equals 2. Okay, now we've added on 1 over 2 squared. And then if we increment again, we've added on 1 over 2 to the third, and one more to the fourth. Now let's stop there for just a bit. So we've kind of rigged up here a very special kind of slider. So this slider has been going up n equals 1, 2, 3, 4, and 5. But if Vicki increments it one more time, so go ahead and hit that up arrow. Oh, it suddenly jumped to n equals 10. So now we have the sum of k equals 0 through 10. And if she increments again, now we've kicked into really high gear, and we were looking at the sum of the first 100 terms. And we could even look at the sum of the first 1,000 terms. And now and notice here that we're just getting 2 because we're so close to this certainly looks like it's converging on 2, but that's not a proof. This is actually on a CAS machine, and we've really rigged up this slider to go to the limit. So if Vicki goes one more time, she's actually gone to n equals infinity. And the CAS is actually able to do these infinite summations in many cases. Now, if you're wondering about that slider, gosh, how is that slider suddenly kicking into these different increments, will reveal that it didn't really take much. So Vicki's going to scroll up here. And it turns out what we did here was that slider variable was actually called NVAR, N variable. And we had n variable run from 1 to 10. And when n variable was equal to less than 6, like 1 through 5, we just let n be that number. But as soon as we got to 6 and higher, notice that that when statement says, okay, when it's not less than 6, but it is less than 9, let's go 10 to that power, n var minus 5. So that's why when we did that increment, we started seeing 10, 100, 1,000. And finally, when we hit n var equal 9, it went all the way to infinity. So it's kind of a way to get actually a slider that increases its speed and can even go to infinity if you've got a CAS. If you're on a non-CAS machine, then you would still be able to do a numerical kind of exploration like this. So let's have a little bit of fun with this. Vicki, why don't we go ahead and crank the n down to 1 again. And why don't we try interchanging the k and the 2. So instead of 2 to the k, how about k to the second? Okay. Oh, and I'll tell you what, let's edit that k equals 0 to k equal 1. We really need to start. Yeah,
yeah,
okay.
We do.
There we go. Okay, that didn't really make sense with k equals 0. Okay, great. So this is just going to be the sum from 1 to 1 of 1 over k squared. So it'll just be 1 over 1 squared, or 1. And as we increase this, okay, that's going to be 1 plus a quarter. Makes sense. 1 over, and then that's going to be 1 plus a fourth plus a ninth. So we're doing the reciprocals of the squares. And so I'm going to let Vicki just go ahead and start cranking that up. And it's growing, but growing slower. Now she's going to hit it all the way to infinity. And that's a really kind of a neat, surprising result. It's I think this is due to Euler, I believe. It's a pretty interesting result that somehow the square of pi came into play there. Now I'm going to have Vicki just leave it on infinity.
Oh, you want me to leave it on infinity?
Yeah, go ahead and leave it on infinity and change the 2, the power 2 to a 4.
Oh, you want me to go to 4? Okay.
Yeah. Oh, look at that. That series actually converges, but it involves pi to the 4th. And I wonder about k to the 6th if we tried that.
And if you think about it, this is just fascinating, and it should be very interesting to the students to see that someone might be able to figure something like this out, and that it's, just the math becomes so powerful.
Right. Yeah. And I'm now going to have, I think Vicki almost did it a little while ago. Now I'll go ahead and have her try 3. And it's just spitting the same series back at us. And here's the fascinating thing. So this is an unknown. Oh, well, well, here's something we can know with our students is that 1 over k cubed, those terms are going to 0 faster than 1 over k squared. And so if that series, 1 over k squared, converges, the 1 over k cubed series should converge too. What this is, the CAS is telling us is it doesn't know what the sum is, though. And in fact, this is still an open question. No one, we know that 1 over k cubed, that series converges, but we don't know what it converges to. You would like to think pi cubed was in the picture somewhere, but we really don't know. Vicki's tried 1 over k to the 5th. Same thing there. So quite interestingly, the even powers of k, the reciprocals, those converge, and we know what they converge to. But here, the odd power, the reciprocals of the odd powers, is kind of an unknown thing. Tell you what, let's try a little different thing. I'll tell you what, first go ahead and crank her down to
1. Okay.
Yeah. Okay. And why don't we do k equals 0?
All right.
As the first, and let's try 1 over k factorial.
Okay.
Great. Okay, so here this would be 1 over 0 factorial plus 1 over 1 factorial.
Which would be 2,
up to
so
2.
we're good.
And as we start cranking it up, okay, now we've added on 1/6 and 1/24, and it's adding up.
1 over what, 120 now?
Oh, look at that. That number is looking
familiar.
And this one is really kind of neat as you go ahead and go to,
This was pretty fascinating. I don't know if I can make it. I had trouble.
Yeah, it's that arrow down there. I think you're in there now.
And this is just like mind-blowing, but this is how the calculator reported that value.
Yeah.
I'll go back up to this. Whoa. All right, so you ready to crank it up one more time?
Look at it, infinity, yeah. Boom. And there it's giving the exact limit of that series, which is very neat. Okay.
I'm just imagining some oohs and ahs in the audience that we can't hear.
This is really, I just love using this in the classroom in terms of, illustrating what's going on and getting these kind of what-if questions, so the things you can try. So this is, using kind of the full, on a numerical series, that being able to go to infinity, that's something you would need a CAS for. But even with the non-CAS machine, you can do a lot of numerical explorations with series, at least looking at partial sums and getting a sense for convergence or divergence. So maybe, what do you think, Vicki? Should we move to the 84? And kind of,
yeah, let's do that. Right. Okay, so on the 84, we have kind of started a set of lists here. So in L1, we have the same values that we had on the TI Inspire. So we have 0, 1, 2, 3, 4, et cetera. And so what we want to do in the second list, L2, is sort of build those sequence values that you saw on the Inspire a second ago. So I'll go up and highlight L2 and press enter so that we can now edit this. And I want to enter, try to make sure I enter the right thing.
Sure. So let's say we wanted to do a geometric series of 1 over 2 to the k, where k values are in list 1. We can actually just write that as 1 over 2 to the L1.
So I need to get L1, so second one. And so this should produce that same list of values that we saw on the Inspire. So I'll hit enter, and there we go.
Though here they are they're reported in decimal form, but that is our 1, a half, a fourth, an eighth, and so forth. So, okay, so that's our sequence list, and now Vicki's going to show us how to do the partial sums.
Okay, so we want to add what do we want to do, Tom? Add.
So we'll go to the list menu, which is, there we go, blue second stat.
Oh, yeah, cumulative list, operations.
And then we have operations, one of which is that cumulative sum, which is exactly what partial sums gives us. So the cumulative sum of L2.
L2.
Yeah.
There we go.
And now, again, in decimal form, it's showing us now the partial sums. So there's the 1 plus a half, the 1 plus a half plus a fourth, and so on. And again, in decimal form, I think one nice thing about the decimal representation is convergence kind of is very visible when you put decimals in you line up that decimal point. You can see the convergence here. Okay. Want to be quick to add that kind of that numerical evidence of convergence isn't a sure thing. So for example, we might try another list. Let's see, list 1. So we're starting at 0. I'll tell you what, Vicki, let's redefine L2.
Okay. Righty. Oh.
And let's make it equal to 1 over, in parentheses, L1 plus 1. and I'm hoping that
should have cleared it.
Oh, that's all right.
Yeah, it would have been much faster. I just figured I could hit delete while you were talking. Okay, what am I defining it as?
So 1 over the quantity, so parentheses.
Okay.
And let's do L1 plus 1. So the list L1.
Okay.
And I'm hoping this will work. Let's see. Okay. I had to adjust by 1 because since I had 0 as that first element there, what I'm trying to do is just get the series of the reciprocals. So this is 1, a half, a third, a fourth, of course rounded to decimals.
Right.
And I think L3, you didn't have to even do anything to it. It's already, let's see. I guess no, we do have to do. It's still showing us the geometric, isn't it?
Yeah,
okay.
Because what it does is.
Yeah. It just replaces it with those values. Okay.
Yeah, it'll actually be easier for me to clear that list the correct way rather than what I was doing.
Okay, there we go.
All right, now we go back.
Now when we go back to the list.
Now it's cleared, okay.
And here we could just do the cumulative sum again. So we could go into that list menu and...
Nope, I did the wrong thing.
So I think we need to do second stat.
Yep.
Yeah. There we go. On operations, cumulative sum.
There we go. And we need L2. There we go.
And excuse me, I think just the point I'm making here is the harmonic series, the sum of the reciprocals. That's a divergent series, but it grows so slowly that if you were to look at partial sums even out pretty far, they might suggest to you that it's converging, but it isn't. Actually, those sums do continue to grow without bound, even though, we're even up through the 10th term, we've only just barely gotten above 3 in our partial sums. Yeah. And so the harmonic series, I think it's one of those that students really want to be familiar with it because it's such a key series in terms of being an example of a simple series that diverges even though the terms go to 0.
Right, and it also shows up very often in questions that are on the AP exam, especially when the students are working with testing the endpoints for an interval of convergence. And so they need to be very familiar with the harmonic and the alternating harmonic series.
Right, yep.
All right, so that's sort of simulating what we were doing on the TI Inspire with the list. I think you will see that the advantage of the the TI Inspire would change, the list would change. So like this list 3, we had to actually delete it and start over, but it's not that hard to do on the 84. And I think the 84 does a very good job of demonstrating what these series are doing in a very similar way to the Inspire. The Inspire is just a little more dynamic. So one of the other things that we want to look at now is this idea of the Maclaurin and Taylor polynomials and how they are converging to a particular function and what the interval of convergence might be. So we're going to kind of change our tune here a little bit, and we're going to do some graphing. And we thought maybe we would start with the geometric series 1 over 1 minus x, which is actually just a rational function. So 1 divided by 1 minus x. And let's just first look at this graph. And so we know that, and I've already kind of got a window adjusted here a little bit, so we know that this particular rational function has a vertical asymptote at x equals 1. If you are familiar with the geometric series of 1 over 1 minus x, you know that we are actually just building a polynomial where the first term is 1, and we're multiplying by x each time. And so our first term is 1, our second term is x, our third term is x squared. But since we're multiplying by x and we want this geometric series to converge, then we know that the absolute value of x has to be less than 1. So if you think about what that means here is, you know, like we're going to actually look at the interval of convergence for this, and we're going to kind of build some polynomials to visualize that interval of convergence. So I'm going to go back to y equals, and Tom, stop me any time along the way here.
Okay.
Do you want me to just do the first, like the constant term, so we can talk about it a little bit?
Sure.
Or do we want to do the tangent line, the linear approximation first?
Well, let's go ahead and do, why don't we do the first three? How's that? So
okay, all right, so 1 plus x, oops, that's not
Or I was
x.
thinking we could do 1 plus x in y3.
I gotcha, okay.
And
so
then 1 plus x squared in y4. How's it?
Gotcha, okay, so 1 plus x. And
Well, that'll be the 10. Do you want to do just 1 by itself, or?
We can.
Okay.
All right. If fumble fingers can get things to work out, I feel like I'm deleting the wrong thing. All right, 1 plus x, 1 plus x plus x squared. Okay, so we'll hit graph, and there comes our
There's our constant
and our linear
line.
and our quadratic. And maybe I want to change that window a little bit. So let's actually go from -2 to, oops, that was really good. -2 to about 2. You think that would be a decent window?
Sure, yeah. Let's try that.
All right, let's look at that. So this is a little better window. Okay, so there goes our constant, linear, quadratic. And so think about this idea that the absolute value of x is less than 1 is the interval of convergence, which means x is between -1 and 1. And so you can actually, just with that quadratic, begin to visualize how these terms of this polynomial, if we keep adding terms, might look more and more and more like the blue graph, which is our original function, 1 over 1 minus x, as we add terms to those polynomials. Just from the quadratic, you can see that that interval of convergence might be from -1 to 1. But we can go add a few more terms. Do you want to do that?
Well, let me say something maybe real
okay.
quickly here. Is in the course description, that very first screen that Vicki was discussing, it made a comment about making this connection of the work on Maclaurin and Taylor polynomials to the tangent line. And the idea is the tangent line approximation is actually a first degree Taylor polynomial approximation. And so it's just now we're generalizing by going up higher degrees. So this kind of magenta graph here, which is the parabola, if we think of that tangent line as being the best linear function approximation at that point, the second degree Taylor polynomial is the best quadratic approximation to the function at that point. And we can see that we get a little bit better fit over a little bit larger area. As Vicki is suggested, though, because of that asymptote at x equal 1, we're not going to be able to expect these polynomials to, as we go up in degrees, to be a good approximation much outside of that interval from -1 to 1. So, yeah, let's go ahead and...
all right, I'm just going to add to the magenta graph just to keep from having a bunch of things here. So.
Too busy.
Yeah, get a little busy there.
Yeah.
All right, so we want plus x cubed plus x to the 4th. Do one more? Maybe
sure.
x to the 5th? I'm on a roll now. Okay, so let's hit graph. So the magenta now will be a best...
Quintic.
Quintic, yes. Quintic. Oh, look.
Oh, and look how, and you can see it's not a good approximation outside. Once we get a little bit outside of that interval from -1 to 1, especially to the left of -1, it's not good at all. And of course, it's going to be hopeless to the right of +1 because we're on a completely different branch of the graph of the original function there. So,
but I just think this visualization of seeing these graphs for the students, and of course, there's going to be some student in your room that's, 10 minutes later, they're still adding powers of X and going to show you what they've got. You may have actually gone into an entirely different example, but they're still over there adding some terms because they want to see how well they can make their new polynomial fit the graph of the rational function, 1 over 1 minus X. But, they get real interested in it and involved with it, and I think that's what's really good about getting this visual representation to the students. All right, do we want to look at another function on the 84 very quickly, and then we'll move into the Inspire again?
Why don't we go ahead and go to the Inspire? I'm thinking
okay.
that given.
All right, so we'll go back to the Inspire. So now there's actually an activity. You can find this activity on, I'll go to the first screen. It's called Taylor Polynomials, and I think it's on the Calculus Inspired of the Math Inspired site. So it's there. There's probably some nice little teacher resources and student questions that could be asked, but you can do a lot with just this TNF file. This is just describing what we can do. We can define f1 of x, which is going to be our function. We can use the sliders to change the degree of the Taylor polynomial, and we can even slide the point A so that we can center so it starts off with a Maclaurin polynomial centered at x equals 0, but we can slide that point A so that we're looking at Taylor polynomial expansions. All right, Tom, I think this one starts with sine of x.
Okay, so our red graph here is a graph of sine x, and then the blue graph is a graph of the Taylor polynomial that is expanded around the point, the x-coordinate of the point A that you see there. And the degree is operated by the slider in the upper left-hand corner. So notice the degree here is 0, and what that's going to give us is just a constant function value. So sine of 0 is 0, and that's why we're seeing the y equals 0 line. Now Vicky's going to grab the point A, and she'll have to tab, there we go. And as she moves A, it's now, we're getting a new Taylor polynomial, though this is a very simple one. It's just a constant function. And what it is, it's the constant function through the point on the graph that's directly above or below A. Okay.
All right, so we'll get back close to 0. All right.
Now, if Vicky cranks that up to n equals 1 and then grabs the point A again.
Oops. There we go.
Now we basically have this sliding tangent line approximation. Now, if Vicky kind of leaves it at A equals 0, and then instead of playing with A, just starts cranking up the degree, n equals 2, that's interesting. It didn't really change. But n equals 3, we see a cubic. And if we go to n equals 4, n equals 4 looks kind of the same. But n equals 5, now we got a quintic. And by the way, I mean, I know I'm talking to the choir here, but if you think of the sequence of Taylor polynomials for sine x, each one is an odd degree. The even degree ones, there is no extra term that's added on. So the fourth degree Taylor polynomial approximation of sine x at A equals 0 is the same as the third degree because there is no fourth degree term. I'll tell you what, though, Vicki, go ahead and go back down to 4.
Okay.
Okay, that looks like a cubic, That's because there's no fourth degree term, but if Vicki now grabs A and moves it.
Yes, this is going to be interesting.
As she gets away from A equals 0, now we can see this really is a fourth degree, because now we do have a fourth degree term. Okay. Now, what's fascinating to me is, Vicki, go to about A equals 2. Okay, so this is a fourth. Yeah, that's good. I think what's interesting here is, that's okay, that's all right, that's fine.
Okay.
That quartic is looking like a really nice fit for almost close to a full period, not quite. And this is an example of this sequence of Taylor polynomials. The radius convergence here is actually infinite. It'll actually, as the degree goes up, and why don't we go ahead, just for grins, crank up the degree. And you can see that we're getting to where it's almost on the entire screen. So here's one that, now if we had a wider window, we would see, yeah, it does eventually. But if we kept cranking this up, that fit would expand wider and wider and wider, and it actually converges for all real x, which is really kind of neat. And what I tell my own students about that, it's as if the Taylor polynomial is built out of the data that we have about the function at a single point. So if we know the value of the function, its first derivative, its second derivative, its third derivative, and so on, at that one point, there are cases where that determines the entire function. So it's almost as if that point is like the DNA of the function, it has all the information for the whole function.
So if you wanted to change the function, you basically would press tab, except not right there. And if you notice, F2, which is the Taylor polynomial, is actually being built with a command, Taylor, that is on the machine. And there's our graph sin x that we have in red, and then our Taylor in blue. So if you wanted to change this to maybe e to the x or whatever.
How about, why don't we try natural log of x?
All right. All right, I need to move, let's see. So we need to move A.
Yeah, so you're moving to 1.
And I probably should crank this back down again, so hang on. See how fast I can click through this. All right, so there's our, do you want to do it centered about x equals 1? Is that good?
Yeah, that's fine. That's perfect. Yeah.
Okay, so there's our constant and our tangent line and our parabola and cubic. And I just love how this dances.
So I think something really fascinating here is that Vicki and I were both at a T-Cubed conference. Was it just last weekend?
Yeah, I think it was.
Yeah. I saw a talk by Steve Kokoska. He's a T-Cubed instructor and former chief reader for AP Calculus. And he gave a presentation where he talked about the radius of convergence and that theorem that there actually is a radius of convergence, that the domain of convergence for these power series is going to be at that center point A, but it will extend an equal amount to the left and to the right of A. So something like natural log x, which has a vertical asymptote at x equals 0, well, that kind of tells us there's no way we can go to the left of 1 more than 1 unit because we're going to hit an asymptote. But look to the right of A, there's lots and lots of space there, but the convergence ends at 2. So notice how there's that polynomial is not a very good fit at all as soon as you get past that radius convergence. To me, that really brings that notion alive.
And I think it honestly helps the students. An example like this where you know to the left of 0, not happening. So you know that that distance from 0 to 1 is 1 unit. So they get a better understanding of this radius of convergence from the centered point and kind of what it means. And this example really brings that out when they watch that building of that 19th, 20, 21. It's very visual to the students, and it helps them understand that idea.
Mm-hmm.
All right, let's go. We're not going to go back to the 84. We did 2 little activities with it that paralleled pretty much the 2 TI-inspired documents that we've shown you. But we want to go to one more TI-inspired document that you would need the CAS to run, and it's very interesting. And so this one is called CAS Taylor. And Tom, I've already got it on the second page, which is the page
that's fine.
Is pretty important here.
Yeah. And I think all this, there's no like special program here or anything like that. What's been done on a notes page on the Inspire is a function's been defined, f of x is e to the x. And then the second function is the Taylor polynomial for f of x centered around 0. And then there's a little slider that'll crank up that degree of n. But the reason we've put this page together for you is that using a math box, we can actually have the slider, you can see the symbolic results of doing a Taylor polynomial. So the 0th degree, this is the first degree, that would be the tangent line approximation for e to the x at 0. And as she cranks this up, we can see the Taylor polynomials being built term by term. Okay. There's no question that, this is a Taylor, this Maclaurin series, a Taylor series about 0. This is an example, one of the ones that students really should know by heart.
Right.
And certainly students are going to be expected to be able, given a differentiable function, be able to, by hand, crank out the Taylor series. So certainly that's something you're going to want your students to be adept at doing that. I think, though, in terms of getting across some of these visuals, and Vicki is pulling up this pane, and then this is similar to the picture we saw before, is as she's cranking up the degree of these polynomials, it's graphing both the original function and that function g, which is a Taylor polynomial. Here, the kind of nice thing is there's also the symbolic form up there.
Yeah. So essentially the bottom screen is what you were seeing on the previous document, but now it's enhanced by the actual polynomial that's being built. So, oh, I got it kind of big there.
Yeah, a lot of terms.
Yeah. All right, Mike, we haven't stopped and even talked about questions. We've been so excited about showing all this great stuff to everybody. So I think we're kind of at the end of what we're
I think that's a good point to
so,
turn it back over to Mike.
Yep. So it's headed your way, Mike, and I guess we need to look at some questions and see if there's some things we need to talk about.
We actually just got one that maybe we could talk about right now. Jeffrey mentioned, is the Taylor series how devices calculate other functions like sine?
I don't believe that's used internally on the TI calculators. So for sine and cosine in particular, I think there's a different approximation technique, but I think it's really fair game, and I do this with my students, is I'll tell them once they see Taylor polynomial approximations, they can imagine that the calculator, whatever it's doing, could do something like that. Because to calculate a polynomial value, you're only doing basic arithmetic, right? You're just adding, subtracting, multiplying. And so those are things that are easy to compute, and yet we're able to approximate very closely these transcendental function values like that. So the answer is no, it's not using Taylor polynomial. Oh, I'm sorry, go ahead, Vicki.
No.
Yeah, the answer is no.
Yes, the answer is no. But I cannot remember right off. I think I have it written down somewhere what is being used internally in the calculator, but I cannot recall it at this moment.
Thanks, I appreciate it.
that all our questions?
I think that's the only question I saw, but feel free to look through and see if I missed something.
Okay.
I don't see anything.
As we begin wrapping things up, again, if you do have any last-minute questions, please feel free to get those asked. I know Vicki and Tom are going to be looking through now to see if they missed something, so certainly if there's any last questions, hopefully they can get to them. If you visit our website, education.ti.com, earlier Vicki had mentioned where the Taylor TNS file for the TI Inspire can be found. I just want to show exactly where that is located on our website. So go under Activities and Math Inspired, second choice down. On the left-hand side, there's a Calculus tab, and there's a whole bunch of really great calculus concepts, including series and Taylor polynomials. So again, these are all free and run on TI Inspire software. Earlier I posted a link in the chat window for the ability to download the software for free as a trial version, so maybe it's just something you want to play with. I know someone mentioned earlier in the chat window that sometimes the visuals are just so important when learning mathematics that I couldn't agree more. So again, these activities come complete with student and teacher notes, and sometimes that's really great to use with their students. Other times, I just like using the visuals. They're enough for me to get my students thinking and engaged. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, so we really hope you share your thoughts in the post-webinar survey. We're excited to announce that at the beginning of next month, we should have live on our website locations, dates, and titles of workshops of over 50 different T-Cubed summer professional development workshops that are going to be offered across the United States. So please stay tuned, but you can expect to get workshops that focus on the 84, the TI Inspire, maybe even specifically to the TI Inspire CAS. Workshops that are going to focus on calculus. So please visit our website at the beginning of April to see if there's a workshop nearby that you might be interested in. We are giving away tonight one lucky winner a free T-Cubed summer workshop registration. And tonight's lucky winner is Mimi Corcoran. So Mimi, congratulations. We'll be in touch over email in the next couple of days to give you a little more information, but we really hope to see Mimi as well as everyone else at T-Cubed Summer Professional Development Workshop. Feel free to stay connected using any of the major social media outlets. We'd love to hear your comments and your thoughts. To receive a certificate of attendance, please click the link in the chat window. Also listed is a link for the documents that were used tonight by Vicki and Tom. If either of those links aren't working for you for any reason, have no fear, you'll automatically get a follow-up email in a couple days, and in that follow-up email will be a link to the recording, a link to the certificate, as well as a link to the documents. And if you happen to be watching this on demand, please go ahead and copy that link into your favorite browser to receive your certificate. Once we end tonight, if you have any additional questions or need additional follow-up, please feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. Thanks so much, Vicki and Tom, for everything you shared tonight. I really appreciate it.
Thank you.
Thank you. I did see, a question that, if we've got time, I'll try to answer. So.
Sure.
Okay. So I think this is from Alan. He asked about why texts use natural log of the quantity 1 minus x for Taylor expansion. rather than the example we looked at, which was just regular old ln of x. And I think the answer to that is to illustrate a couple of things. If you do ln of x, you can't do an expansion around 0 since it's undefined, and so they'll shift it for that. But the other reason goes back to Vicky's original example of 1 over 1 minus x, which is a geometric series. And so starting with that, you can use integration to get to the series for the natural log of the quantity 1 minus x. So that illustrates how you can take a known power series and work to another one using calculus by integration or differentiation.
Thanks so much, Tom. Again, thanks everyone for joining us tonight. We hope to see you back online next Tuesday. Have a great night.